Scuba diving is a popular recreational activity. Scuba divers are able to explore deep water features like coral reefs and aquatic life. Swimmers and non swimmers have access to this beautiful environment made possible from the understanding of physical concepts of buoyancy and pressure. At ground level, we are exposed to the ambient pressure of one atmosphere exerted by the air around us. Water is a more denser medium than air, and the movement of the diver in this high density medium is restricted. Without proper understanding of the buoyancy, driver weight distribution, and the gauge pressure of the breathing equipment, staying efficiently underwater is impossible. The interactive 3D module for visualization of physical concepts of pressure, Bouyant Force, etc. is made available at the website effectual.github.io under the topic Thermodynamics. So, how deep can a scuba diver go safely? Not a large depth. Fluids over the diver exerts immense pressure on them. For the driver to breathe the air from the compressed cylindrical tank, pressure gauge needs to be maintained slightly higher than the outside fluid pressure. Only then the air can flow and the driver can breathe underwater. As seen here, every increase in depth of 10 meter, the pressure underwater increases by 1 atmosphere. Two objects of similar shape but one sinks and other floats is explained by the density of the material it is made up of. Objects having density lesser than the fluid floats. Steel is a denser medium, almost 8 times denser than the fluid water. Density is defined as mass per unit volume and is represented by the Greek letter rho. Now, let's look into the formula for pressure. Pressure is defined as the perpendicular force acting on a given area, as depicted here in this animation of a syringe. The perpendicular force acts on a small area, inserting the medicine into our veins. When you select a column of the fluid of height h and surface area A with a given mass m, it exerts a downward force of mg. The air molecules on top of the fluid exerts 1 atmospheric pressure, again in the downward direction. So, the net downward force is equal to the sum of these two forces. Replacing mass with density times volume, we obtain a new relation for pressure at a depth. This pressure varies with the depth of the fluid. Now, let's look into the visualization of Bouyant force. Here is a spring in equilibrium. The weight is counterbalanced by the tension on the string. When fluid is added to the container till the object is fully immersed in it, we see that the spring weighs less, shows a weight which is lesser than the previous one. This loss is due to the Bouyant force acting upwards. Archimedes' principle states that the upward Bouyant force that is exerted on an object immersed in a fluid, fully or partially, is equal to the weight of the fluid that the object displaces. Archimedes' principle is a law of physics fundamental to fluid mechanics. The scuba diver counterbalances the Bouyant force using Bouyant weight in his jackets. Bouyant jackets helps the diver from staying under deep sea and later in resurfacing. In next video, I will cover Pascal's law, speed of flowing liquids, etc. Visit the website for physics 3D interactive simulations and see the effect of visual learning the effectual way.